binary tree structure in array. Yeah. Yeah. So after we talk about a lot of background information, the motivation, why we need to do that. Yeah. Now we are ready to construct binary tree structure in array. Yeah. So some challenging step, because we want to specify parent-child relationship in a simple way. We don't want to use pointers. We don't want to use references. We want a simple way to address the parent-child relationship. Think about what is a simple way. So without using pointers, references, we have some simple, straightforward way to identify parent node, child node. So which node is the parent of this child node? Which node is the child of this parent node? Yeah. That information. Yeah. Yeah. There is a simple solution, very simple solution. Yeah. So after you see it, so you will feel it's so easy. Yeah. Where is it? Yeah. Yeah. So let's look at the answer. Okay. All right. Why my remote control does not work? Okay. Oh, yeah. Why the receiver? The receiver is gone. Okay. Oh, here. Yeah, I pull it out. Okay. All right. Yeah. Yeah. Oh, what's that? Yeah. So all right. Yeah. So we did a little bit last time. Yeah. Yeah. So, okay. Yeah. Yeah. Heap property. Yeah. But heap property. Yeah. Relationship among heap nodes. Yeah. 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 Because that previous topic we didn't talk about the structure. Yeah. All right. Here the structure. Here we get detailed information of the heap structure. A binary tree is stored in an array by imagination. Yeah. Yeah. You can only imagine a binary tree. So there is no concrete binary tree. Okay? So, imaginary. Yeah. All right. So the node located by its index, the location, array, all the locations specified by their indices. Okay? So that's the only way you can access array elements. Yeah. Relationship between two nodes. How do you describe relationship between two nodes? Using their indices. That's the only way. Yeah. Indices. Yeah. Locations. All right. So now we need to look at the relationship between two indices. So we can define. Yeah. So we can define that relation. Yeah. All right. So the parent-child relation, a typical parent-child relation. All right. So look at the, this typical structure in a binary tree. Yeah. P corresponds to the parent node with index I. This I is the location in the array. Yeah. Then left child, which node we select as the left child of this P node? We select a node with index 2i. 2i. Double. double the original index I. Original parent, we assume its index is I, so its left child, we go to the location 2I and use that element, assign it as the left child of the P node. Yeah. Then right child, we go to the location 2I plus 1. If we can find one, sometimes you may not be able to find one. If you can find one, so that one, we make it right child node of P, current P node. That's the relationship. Okay? Yeah. So that's the way we define parent-child relationship. Yeah. Then, if we do this everywhere, okay, yeah, the whole array, yeah, the whole array everywhere, then you can imagine a binary tree is there. Yeah. The binary tree is there. Okay. The connections between the node, among the nodes, connections based on the indexes. No pointers, no references. Yes, good question. Starting from 1, not 0. Yeah. So the next question, yeah, we will get there. Yeah, good point. Yeah. I cannot be 0. Because you double 0, still the same node. Yeah. We have to, all these nodes must be different. So A of 0, the first element in the array, is never used. Then starting from 1, yeah, everything works fine, yeah, except the first index, first 0 index node. Yeah. All right? So then you can see, yeah, it works perfect. Yeah. So nothing wrong. Yeah. Yeah. But you need to modify your original array. So when you define array size, you cannot use the first element A of 0. So you may need to use position indexes from 1 through n. 1 through n locations. Then you can use this parent-child relationship. Okay, yeah. All right. Then, 2 types of heaps. So now you have the binary tree structure. Now we want to specify more properties for the heap. Yeah. Max heaps and min heap, minimum heaps. Corresponding to, when we organize our binary tree structure, do we want to put the maximum at the root or minimum at the root? Right? 2 different types. So max heap, minimum heap. Yeah. All right. Max heap property. We define max heap property. Okay. So for all nodes with this property, A of I, the value A of I, greater or equal to the values for its left child, A of 2I, and also the value of its right child, A of 2I plus 1. 2I plus 1. Okay? Yeah. So then, all right, so then, everywhere, okay? So you get a max heap. If there is one place these 2 inequalities not true, we cannot call a max heap. Okay? Similarly, for the min heap, minimum, min heap, yeah, so just the opposite. A of I less than or equal to the value of its left child and the right child. Okay? Yeah. But when you have max heap or min heap, yeah. So for example, yeah. So for this class, we just use the max heap, yeah, because min heap similar, so we do not need to, repeat our discussion another time for the minimum heap. Yeah. So the max heap, yeah. Then the value between left child, right child, which one larger, which one smaller, it's not important. Okay? Yeah. So here, we do not say anything about the values between left child, right child. Yeah. Either one can be larger, smaller. Yeah. All right. So then we have this concept, max heap concept. Yeah. All right. Let's look at a max heap example. Yeah. All right. So yeah. Look at this heap, yeah. The structure. Okay. All right. Yeah. So I give you the index numbers 1, 2, 3. These are all the indices, array indices. Inside the circle, the number, that's the values of the elements. Excuse me. Yeah. All right. So you can see. Now we can use the max heap property to check. You can check everywhere, right? Yeah. Everywhere you have that max heap property. Yeah. No violation. Okay? All right. So then the underlying array, yeah, so although you see this one, but in the array, you need to store in the array structure. Yeah. That the first element, we do not store any element. 0. Position 1, 16. And this node, 2 child, left child, right child, left child value 14, right child value 10. Okay? Yeah. So then the node number 2, 2 child nodes, left, right, 8, 7. Okay? Node number 3, 2 child nodes, left, right, 9 and 3. Okay? Next one, node number 4, left, right child, 2 and 4. Okay? Then node number 5, only left child. Value 1 at position 10. No right child. It's a typical max heap example. Okay? Yeah. Yeah. All right. Now, maintaining the heap property. If something is, because you need to insert a new element. After insertion, the max heap property violate somewhere. Okay? Some places there is a violation. So you need to fix it. You need to fix the violation. Yeah. So we do this maintaining work. Yeah. When the heap property is violated due to some operations, insertion, deletion, etc., how to fix it? Here, yeah, let me describe, the typical steps to fix one violation. Yeah, all right. Here, assume we look at this triangle location, P, L, R. These 3 nodes form this little local triangle location. Yeah. 1. Violation occurs locally. Yeah. So there is so those 2 inequalities not true. Yeah. At least one of the 2 not hold. Yeah. Yeah. And here we assume left subtree max heap, right subtree also max heap. Violation occurs starting from P node containing L node, R node. Yeah. But the subtree below L, we assume max heap. The subtree below R, we also assume max heap. Yeah. All right. Local fixing operations. And we also need to check violation globally. Yeah. Because if you fix the violation locally, the violation could occur in other places. So you also need to check violation other places. Yeah. So globally. Yeah. All right. local heapify operation. Let's look at it. How to fix violation locally. So we call it local heapify operation. Yeah. What's that? It's a recursion approach. Yeah. Yeah. All right. Yeah. So now we write the code to check the values in these three nodes. Yeah. And we want to make sure those two properties, parent-child relation for max heap property, those two inequalities hold. We want to make sure. Okay? Yeah. Here, so let's check. First, let's compare if A of I less than A of 2i, it's a violation, right? Because for max heap, A of I should be greater or equal to A of 2i. So this inequality, if condition, tells us there is a violation. So we need to fix it. We need to do something to fix it. Okay? When that happens, we take a variable called the largest here. Largest is a temporary variable. Okay? Temporary variable here, we assign left child location 2i to this temporary variable, largest. Yeah. Later we will use this value. So largest variable, assign it. All right. Else, yeah, else, if else means A of I greater or equal to A of 2i, right? Else. Then no violation here. So the largest, we assign I location to the largest. Yeah. Because we do not need to change the largest. Largest occurs at I location, so we do not change it. Okay. All right. Then we check the right child. For the right child, if A of largest, this time we compare A of largest. Yeah, because the left child could be the largest, right? So this time we use A of largest to compare with the value A of 2i plus 1. If A of largest less than A of 2i plus 1, another violation. So we need to fix the second violation. The second violation, we just assign 2i plus 1 to the largest temporary variable. Because that right child, that value should be placed in the P location. Okay. All right, so next time we update the largest variable, temporary variable, its value should be 2i plus 1. Okay. All right. Then, the next step, we need to update. We need to, yeah. First, we check if the largest not equal to I. That means you make change. Yeah. If largest equals I, you do not need to change anything, right? No violation. Yeah. So you need to check if the largest not equal to I, then there is violation. Okay. So you swap A of largest with A of I. Sometimes could be the left child node, sometimes could be the right child node. You swap, one swap operation. Don't do two swap operations. Okay? Don't do two swap operations. Here, you do one swap operation, you get it fixed locally. So this is a local heapify operation. Okay? Yeah. Local heapify operation. This is a simple solution. This is a simple solution. Okay? All right. Yeah. Some people may ask question like this. Why not? So when we do the first comparison, if we find a violation, how about we just swap these two values? If we detect the second one, then we just swap. Some people may ask question like that. If in that way, you do two swap operations. Right? Here, this method, we only use one swap operation. That one uses two swap operation. Think about, we want to reduce the number of swap operations. Because swap operation, that means data copy, right? Data copy. Yeah. Sometimes each node, you may carry a lot of data. Because, for example, if you store one object at each array location, one object, the object could be large, could be small, right? Sometimes the object could be very big, okay? If the object is big, when you do swap, you copy a big object from here and there. It's not good, right? Now you do two copies. Yeah. So what we want to minimize the swap operation, okay? So even the object is very big. Yeah. So you reduce the, swap operation on big objects. So that's the reason. Yeah. If from the code you may feel you have more lines, right? You have more lines. Yeah. Because if you do two swap operation, your code could be short, right? Yeah. Your code could be short. Yeah. But the work you need to do is more. Yeah. If you do swap operation, a lot of work, you do more work. Okay? Yeah, that's not good. Okay? Yeah. So here, I answered that question. So we complete this local heapify operation. Yeah. All right. Next, heap example. Now, we want to build a heap. Give an arbitrary array. It's not a max heap. So you need to build a max heap first. How to build? We run this local heapify operation. We can build. But when you run the local heapify operation, you need to follow some specific order carefully. Okay? Yeah. Otherwise, if your order is not right, then you may mess up. Okay? You may mess up. So you also need to follow the right order to do the local heapify operation. Yeah. So let's see how to do it. Here I use a simple example to show you how to do it. Yeah. All right. Max heapify example. Yeah. All right. Yeah. So here, before we build here, let's fix the one violation. So this gray node tells us at this location there is a violation. So we need to fix it. Other places, no violation. Only this place. So let's fix this violation. Node 4 violation. How to fix it? 14 is larger than 7. So you should do swap between node 4 and node 14. Okay? Yeah. So your first swap, these two. Swap. Okay. After that, you move the gray node down, because the node 4, when you move down, you may have other violations. You fix violation at the original location, but when that dirty node, we can call that dirty node, when that dirty node moves down, it's still dirty. Yeah. So you still need to check that gray node, compare its value with its left child, right child, and this time you need to do another swap between these two nodes. Okay? After that swap, it hit the bottom, right? The bottom level. It hit the bottom, or the leaf level. Yeah. The bottom we call the leaf level, right? So we can call it leaf level, leaf concept. Yeah. Because this tree, you have leaf. Okay? Leaf level. Okay? What are the leaf level? The nodes without child. These are the leaves, all the leaves. Nodes without child node. Okay? Without child, all the leaf nodes. Yeah. This node 4 hit the leaf level, then it's clean, because no more child to worry about, right? Yeah. It is already the end of the search path. Search path. Yeah, you need to search, along some path. It's the end of the search path. Yeah. So it's clean. So you fix that local violation. Local violation, you need to keep track of it. Follow the path all the way down to the bottom leaf level. Then you complete the fixing operation. Okay? Yeah. So that's just the one violation fixing operation. If you have other places violation, you need to, do the local, heapify, max heap. Here, we do not call the local heapify. We call the max heapify operation. Okay, so this is the max heapify operation. Okay, all right, yeah, because it's more than local. Okay, it apply the local operation several times, more than that local operation. Okay, all right. Next, now we are ready, building a heap from scratch. Okay, we need to build a max heap. After that max heapify operation, now we are ready to build a heap. Yeah. All right. So this is the given array, original array. Okay. So no heap structure, no max heap structure. So we need to do a lot of, heapify operation. Yeah. Yeah. All right. So then, first, let's arrange all the elements following the heap near complete binary tree. Let's just, do that arrangement without doing anything. Yeah. Yeah. All right? Yeah. Then, to do the, building heap, the process, heap building process, to do that, we need to run that max heapify operation bottom up. Bottom up. You follow that order. Bottom up. That's the right order. Okay? So here I show you. The first, when you start, the first triangle, local triangle to look at is the last one. The last one to look at. Is there any violation? No violation. So we move to the next one. Okay? The first triangle, no violation. Now the second triangle, there is a violation. So I put a star, so violation occurs at this place. So let us run that max heapify operation to fix it. Okay? One swap, you fix it, right? Yeah, so here, so one swap, you fix it. Okay, all right. After that, yeah, so we move to the next triangle. What's the next triangle? This one. Next triangle. Yeah. And we detect there is a violation. So we put a star there. We need to fix it. So to fix it, swap 3 and 10. So we finish this triangle. Okay? All right. Then after that, the next triangle, so move in that order. Okay? Bottom up, from right to left. Okay? Each level from right to left. Okay? Sequentially. Okay? Sequentially. All right? Yeah. Then to fix this one, swap these two nodes, 1 and 16. But after that, you haven't reached the bottom. You still need to continue to, going down. Yeah. So another one, you fix it. When this one reached the leaf level, the bottom leaf level, then you finish that max heapify work. Okay, local. Yeah. That max heapify work. All right. Then you move another triangle up. Okay. This is the last one. So the last triangle, you are working. Okay. Yeah. So swap between 4 and 16. After that, this 30 node moves down. Another swap between 4 and 14. Yeah. So then another one swap between 8 and 4, reach the bottom. reach the leaf level. After you process all the local triangles, okay, bottom up, right to left, following that order, you get a max heap. You get a max heap. Okay? This time, you have a max heap. You'll make your array, you'll make the given array a max heap. No violation. With a max heap, it's ready to do heap sort. Because when we apply heap sort, we have to make a max heap first. Then we, use the swap operation, max heapify operation, we can do the heap sort. Yeah. Heap sort. Okay? All right? Yeah. Oh, sorry. So we finished part A. So the story, the next, part B. So we have a chance to finish part B today, because we have a lot of time. Okay? Yeah. Yeah. And heap sort, not very complicated. So you will see after we build a max heap, then, the implementation of the heap sort, just a few simple steps. We can get it. Okay? But after that, we need to do analysis. After that, we need to estimate how much cost do we need to do the heap sort. N log n. How to get that n log n. Yeah. All right. So part B, so we have a lot of topics we need to discuss. All right, so let's go there. Part B. Part B, we need to, here first we do preparation for our algorithm efficiency analysis. So all the properties we are learning here for efficiency analysis. Later we will use here. Okay. B.1, heap nodes in each level. So if you want to ask me why we do this, so I'll give you the answer. Because we want to do efficiency analysis. That'll work. Yeah, so let's learn some properties. Basic properties, one by one. Okay. All right. First, number of leaves in a heap. Now, a sequence of properties, we need to get formulas. Okay, so here, the discussion. Given, so here, so let me set up the assumption we are using here. We assume we have a heap with n nodes, n, the number of nodes, n. Okay, so so here you can imagine we use the array location indices from 1 through n. Okay, so that's 0, we skip it, but we still have n. Okay, that assumption, that's our current assumption. Otherwise, so you may ask me, do we use location from 1 through n minus 1 or 1 through n, right? So here, for simplicity, let's say we use the heap locations from 1 through n. So in our formula, it's simpler. Otherwise, n minus 1, so it's not very convenient. Okay, all right. The first question, given n heap nodes, we know total nodes in the heap, n. Question, how many leaves do you have in this heap? We know the definition of leaves, right? So those nodes without child node, without any child node. So we call it leaf node. One leaf node, no child node. That's the definition. Okay? So can you find a formula to give us the number of leaves in a heap? Describe, so Yeah, here. We need to describe leaves. If a node is a leaf, what inequality can we get for a leaf node? For a leaf node, okay? Yeah. There must be some constraint. How do you know a node is a leaf? Yeah. How do you represent a node does not have any child node? How do you know? Given index of an element, how do you know this element does not have any child node? Yeah, twice, double. Yeah. So you double that index location. If that location is out of the range, then it's a leaf, right? If it's in the range, valid range of the heap nodes between 1 and 11. So the valid range, that means I between 1 and n inclusive, right? Yeah. That's the range. But when you double it, it's out of the range. 2i greater than n. 2i greater than n. Then this I node must be a leaf node, right? Yeah, that's simple. Yeah, the range. So we use range here. Okay? Yeah. Nodes without children, the child node, the leaf node without children. Yeah. All right. So here. Yeah. Nodes without children, from this diagram you can see these 5 nodes without child node. Okay? All right. Then parent node A of I, child node A of 2i. But if you look at the 2i for these 5 nodes, they will be out of the range, right? Yeah, yeah. So here we can write 1, the location, the index number, 4, 5, 6, 7, 8, 9, 10. Okay? Yeah. So if you double this 5, it's 10 within the range, right? But if you double this 6, 12 out of the range. See? Out of the range. Okay? Yeah. Yeah. All right. So when 2i out of the bound, yeah, no child. Okay? Yeah. So the condition, yeah, so here, condition for I must be inbound, right? Yeah. I node, yeah, within the bound. But 2i is out of the bound. 2i greater than n. If this inequality holds, the I gives a leaf node. That's simple. Okay? Yeah. So let's solve this inequality for I. Okay? Yeah. Yeah. All right. N over 2 strictly less than I. N over 2 strictly less than I. Okay? What is the smallest of such I? If we know n over 2 strictly less than, what is the smallest such I? Smallest. Yeah, but, you know, this I we know it's an integer. I integer, but I must be, this integer must be strictly greater than n over 2. What's that? What's that smallest I? What's that smallest I? Use floor function, ceiling function. So if you use floor function, ceiling function, what function you want to use for that I value? Right, floor function n over 2 plus 1. Floor function n over 2 plus 1. That would be greater than, strictly greater than ceiling function, strictly greater than n over 2. Yeah. Yeah. Okay? For even, odd, n over 2, this expression strictly greater than that. That's our minimum I value, index value, minimum I value. Then all the other values greater than this one all correspond to the leaf nodes, right? All corresponds to the leaf node. Okay, yeah. So you get the range. So this range, this gives you the range of the leaf nodes. Yeah. The lower bound, the upper bound. Yeah. Yeah. All the indices between these two numbers inclusive for the leaf nodes. Question, how many leaf nodes? Here you get a range, but we want to find the number of leaf nodes. What's the formula for the number of leaf nodes? What formula? Can you see that? N minus what number? Upper bound n, right? Minus some number to give you the number of leaves. But minus what number? That's important. N minus what number? That is important. Okay? Minus this number. Okay? Yeah. One fewer than the lower bound. Not minus the lower bound. If you minus the lower bound, you lose one. Okay? Yeah. Because the lower bound, the minimum, the smallest, that element, you throw away. So we minus the number one fewer than the lower bound. Okay? So that is n minus the floor function of n over 2. This number gives you the number of leaf nodes. For any n, this is the exact number of leaf nodes. Okay? All right. Yeah. Then, this expression, what's the relationship of this expression with the seeding function of n over 2? Correlated, right? Correlated. Yeah. Equals seeding function of n over 2. Yeah. So there is a formula we can prove. So the formula is n, this is the formula. This is the formula. So the floor function of n over 2 plus the seeding function of n over 2 equals n. That's our textbook, appendix 477. You can find this formula. If you want to prove it, that's easy. Consider n is an even number, plug in, it's true. When n is an odd number, you plug in, also true. Then you get a proof. Yeah. So by this formula, we can simplify this expression to the seeding function of n over 2. Equal, okay, equal. Yeah. That's the leaf level. So we finished the leaf level. But that's just one level. That's not enough. We want to look at all the possible levels in the heap. Yeah. Here, regarding this level, many students, so when they understand based on their intuition, because when I did grading, the homework assignments, I noticed that many students, so they understand the levels in a wrong way. So what they understand the level, they understand from top to bottom. Yeah. Top to bottom, so there are some level counting from top, but the concept is different. The concept is different. So when we come from bottom, when we come from top, so the concepts are different. Okay? So when you answer questions, be careful. Yeah. So next, I will talk about the concept. Concept, there is a height concept. Height. Each node, there is a height concept, right? How high? How high? The height number of each node. Yeah. First, what's the height number of a leaf node? What's the high number of a leaf node? Leaf node. Leaf node is the lowest level, right? One level what? Two possible, yeah. So here, leaf level, we have two cases, right? These two cases, right? You are talking about these two cases? Yeah, all right. Although these two cases, but when we say leaf level, we treat it as the ground level, right? It's the ground. Yeah. Although this ground lower, that ground is higher, but they're both ground level, right? Yeah, okay. Then, how about we set ground level, the height of the ground level is 0. How about that? Yeah. Because the height, you start from the ground level, the height is 0. Okay? Okay? Yeah. Then, from there, you count one level above the ground. So this node has one level above the ground level. We call it height 1. Okay? So here, one level above the ground level, we call it height 1. Okay? Height 1, height 2, height 3, and height 4. All right? Going up. That's our definition of height concept. Okay? Yeah. Although it's pretty simple, easy, straightforward, but when I assign questions, okay? Yeah. So, my previous semesters, when I assign questions, quite some students, so probably they didn't follow the lectures. Quite some students, they understand height comes from the root, okay? Root from below, one level lower than the root, they treat as height 1, okay? One level, another level lower, height 2. Yeah, that's wrong, okay? So if you understand that way, it's wrong. Your calculation, your answer will be wrong. That one we call depth. Okay, starting from the root. Root, its depth number is 0. One level lower, depth 1. Okay, 1, depth 2, depth 3. Okay, yeah. So the concept is different. The height, bottom up. The depth, top down. Okay, so two different concepts. Yeah. In this class, I do not ask you to calculate the depth. Okay, I just ask you to calculate the height. Yeah. Given height, how many nodes can you find in the heap with given height? That's my question. Okay? So I do not ask you how many heap nodes with the given depth number. Okay? Yeah. Yeah. All right. Next topic. Number of internal nodes with height 1. Now you know the height concept. Number of internal nodes with height 1. What's the internal node? What is the internal node and external node? That concept. Okay? Yeah. Internal node means all those nodes with a child node. So non-leaf node. If a node is not a leaf node, we call it internal node. Okay? An internal must have at least one child node. That's what we mean the internal node. What's the external node? Leaf nodes. External node, another name of the leaf node. Okay, so when you see the terminology, yeah, you know the same concept. External node and internal node, and the leaf node. Leaf node equals external node. Yeah. All right. Yeah. Now, height 1, yeah, because when we look at height 1, yeah, those nodes must be internal nodes. They cannot be the leaf nodes. Yeah. The question is, how do we characterize nodes with height 1? Right? How do we characterize? How do we write inequalities for the indices of height 1 nodes? Yeah. So let's do the analysis. Yeah. Similar to what we did to get the leaf nodes. Yeah. So we just do a little more work. Yeah. So we we start from there. We just do a little more work. Okay, all right. Look at these nodes. They are internal nodes. Okay, but we want to so internal nodes, they must have at least a child node, right? And at least a child node. That child node we should consider left child node, right? Not right child. Left child, right? Because right child may not be available. For example, this node, this node does not have a right child. So we should not use the right child. So we should use the left child to be safe. Because an internal node always has a left child node. Okay? Yeah. So we can double the index of the internal node. Double that I. If internal node has index I, let's double it, 2i. Okay? Yeah. What can we say about that 2i? If we double it, 2i, what can we say about that 2i? What special property do we have of that 2i node must be a leaf node, right? Yeah. That 2i node must be the leaf node. And we know the range for a leaf node, right? The range in the previous slide, we derived the range for a leaf node. Okay, all right. So let us just start from there. Okay, all right. Yeah. So the number of all internal nodes. Yeah, first, let's look at number of all internal nodes. Yeah. Total nodes and number of leaves n minus floor of n over 2. Number of internal nodes. What's the number of internal nodes? The offset, right? The offset, this number. The floor function of n over 2. Because these two numbers adding together, you get total nodes n. Complementary, okay? Complementary, yeah, all right. Now, we are ready to find the number of internal nodes with height 1. This time, yeah. Double the index, okay? Their children are leaves. We just look at the left child node, okay? All right. So if we double the index 2i, it must fall in the range of the leaves. And this is the range of the leaves, right? Yeah, range of the leaves. Okay, all right, yeah. So that's our starting point. Now we want to find the range for I index. What's the range of I index? Solve the inequality for I. Divided by 2. Let's do divided by 2 division. The upper bound easier, yeah, because the upper bound n over 2, and we want to take the smallest, we want to take the, integer, right? Small, upper bound that integer, okay? Yeah. So we take the, here, floor function. We take the floor function, not ceiling function. Ceiling function out of the range, right? We still want the range within the range. So we take the floor function, not ceiling function. Must be integer, upper bound of this I must be integer within the range. So we take the floor function, all right? For the lower bound, how do you see? Because divided by 2, then take the ceiling function, right? Yeah. So the, the original formula should be, yeah. So the previous lower bound, you do division by 2, then you take ceiling function, right? So that's this one. But this one, you can prove equals this one. You can simplify. Yeah. How to prove it? Yeah, here, I tell you how to prove it. Yeah. Because if you just look at it, it's not easy to see why it is correct, right? It's not easy to see why it is correct. No. But here, let me use our old, in previous slide, how do we show n over 2 floor function plus n over 2 ceiling function equals 1? We use the same way. Here, but we need, because this denominator is 4. Here we need to use m mod 4. We look at the remainder, 0, 1, 2, 3. Let's consider 4 cases. When m mod 4 with remainder 0, let's verify the formula. Next, case 2, when the remainder equals 1, let's verify the equality and so on. Okay? After we complete the verification for all 4 cases, we are done. Okay? Yeah, so we get this formula. So now you see the lower bound has this formula. Okay? All right. So the next question. How many nodes with height 1? That question. How many nodes with height 1 formula? The upper bound expression minus what? Right. Yeah. Skip that plus 1. Okay. Only minus the floor function of n over 2 squared. Skip that plus 1. Okay. All right. Yeah. All right. Yeah. So the answer should be this one. This is the answer. Okay. All right. Next question. Can you simplify this expression? Remember our leaf, after we get that number, we simplify it. Yes. Do you want to use the ceiling function of n over 4 for the simplification? Similar way, but here, if you do that, you should be careful. You should be careful. If you do that, you get inequality, not equality. Okay? Yeah. So in our previous one, that's equality. This one, inequality. Yeah. Because, yes, there is some cases the equality does not hold. Yeah. So you use m mod 4 remainder 0, 1, 2, 3. You can check. There are a few cases the equality does not hold. So we can only use less than or equal to this one. So we get an estimate. Okay? Yeah. All right. Yeah. But this is still useful because sometimes we need to use the estimate. Right? Yeah. Yeah. So sometimes we need to use the estimate. Okay? Yeah. All right. Yeah. Next. Yeah. Can we generalize? Yeah, here we find height 1. Can we find the number of nodes of height h? Yeah. All right. Yeah. So if I ask you the number of nodes of height 1, you should use this exact number. Do not use this estimate number. Okay? Yeah. Estimate not exact. When I ask, because in my questions, I may ask you the number of height 1 nodes. So you use the exact formula. Okay? Yeah. All right. Number of internal nodes with any height this time. Yeah. So we want to use the similar way. Generalize the previous result. Number of leaves. Yeah. So total number of leaves. This number, height is 0. Okay? Then the number of nodes with height 1, this formula. Yeah, range, this formula. Yeah. Height 1. Okay? Can you go another step further? Number of nodes with height h this time. Yeah. Yeah. By induction, so here. Right. All right. So the range, so this is the range. Okay? This range. And the number of nodes, upper bound minus 1 less than the lower bound. So that's the general formula. Okay? Yeah. Height 1, height 2, height 3, all the other heights. This formula. Okay? Yeah. So then, after we get these formulas, it's enough, we can do efficiency analysis. We can do efficiency analysis. Yeah, so today, so we may not have enough time. So all right. So let me just go one more slide. But next time we can close it. So we just need 10 minutes to complete part B. All right. Combine the cost of all heights. When you build a heap, how much cost? So you want to estimate how much total cost when you build a heap. If it's too costly, then this method, we won't take it. If it's too costly, building cost is too high. For example, n squared. If the building cost is n squared, do you still want to, take this solution? No, you don't want to take this solution. Too costly. Okay? Yeah. So the building cost, we want to estimate. All right. The cost of max Heapify for all nodes of height h. Let's just look at the height h, max Heapify. Because if we can do one level, this is a typical level, right? Representative. If we can do one typical level, we can do all the levels. So let's just do one level here. Height h. Height h. Height h. All right. So here. The number of nodes in the height h. Yeah. Remember this formula? That's the estimate less than or equal to, right? Yeah. Number of height h nodes less than equal to this number. And for each node, when we fix a dirty node at height h, what's the cost for each one? Big O of h, right? Because we need to move each step down to the earth, right? Down to the bottom. Down to the earth, right? Yeah. That's each step. Each step, constant number of operations. So big O of h, or big theta of h. Yeah. So if you use big theta, it's fine. Yeah. Big O, big theta. Okay? Yeah. No big difference. Yeah. All right. Each. Then, total h, you do multiplication, right? Yeah, because you have this many. Each one you do big O of h, you do multiplication. Okay? All right. Yeah. So, but you need to collect all the h number from 1 through log of n. Floor function. Floor function, not ceiling function. Floor function. Root level, yeah, floor function. Yeah. Because you leaf level, it's 0. Okay? Leaf level, it's 0. Yeah. So then top level floor function, not the ceiling function. Okay? Yeah. All right. So skip the leaves. Leaves, we do nothing. Leaves, there is no max Heapify cost. No max Heapify cost. Okay? All right. Then H level, each H level, this is the cost for H level. Now we accumulate the cost of all levels above the leaf from 1 through top level. Okay? So our next question, we need to estimate this summation number. We need to estimate. Okay? So we need to do math. We need to do summation. Okay? Yeah. All right. Yeah. All right. Yeah. So let me stop right here. Yeah. Because we do not have enough time to complete